Thank you for joining. I'll be talking about ctbench, which is a compile time benchmarking tool for Clang. So I'm going to introduce myself. I'm Jules Pénuchot. My pronouns are on screen. So I'm a PhD student in the Parallel Systems team, which is a team at the LISN, which is the Laboratory for Computer Science and Numerical Science in Paris-Saclay University. And I'm here to talk to you about a tool that I wrote, which is ctbench. It's actually a set of tools for running compile time benchmarks and analyzing the data with Clang. Okay, so first I want to talk about the way metaprogramming is evolving. So we see a trend on the side of support libraries. We've seen Boost MPL, Boost Fusion, Boost HANA, Boost MP11, also Brigand, and I'm also pretty sure that some people in the audience have their own snippet repository or like headers with some kind of metaprogramming snippets to reuse here and there. So it really shows that people actually want and build better metaprogramming libraries as time goes. And it's actually not just on the library side, it's also on the language side. So with C++, we've seen, well, first type traits with C++11. We've seen constexpr specifier, which is kind of the first way to do metaprogramming using programming constructs that are familiar for, I would say, people who do more mainstream C++. Then we've seen, we've seen if constexpr in 2000 with C++17, which is, well, another familiar construct for metaprogramming. And then with C++20, we've seen more constexpr containers. So this is actually a pretty big deal because this is the first time that we can actually use dynamic memory in constexpr functions. I'm not sure it's very well implemented in all compilers right now. I know that Clang libc++ has some, is a bit late on that, but I think that it's pretty okay on libstd++. And then right now we are seeing other proposals like the reflection proposal and the metaprogramming proposal. So the reflection and metaprogramming proposals are kind of a metaprogramming paradigm shift in the way that we are not using types for computation anymore. If these proposals see the light in C++23 or 26, it means that we are actually getting tools to metaprogram C++ using actual regular C++ APIs. And then finally, C++ might just become self-aware and take over the metaverse, but that's for another presentation. And then on the application side, we're seeing other libraries such as Eigen, which is, well, more focused towards computation. It's kind of the precursor for expression templates for numerical computation. Then we've seen Blaze, which improves upon Eigen. And then we've seen other libraries that are specific to other domains, such as CTRE by Hanna Duzikova. So CTRE is pretty massive because it actually allows people to compile regular expressions at compile time. So basically it means that you have pure compile time, pure regular expression code in your assembly, and you're not dealing with interpreting an abstract syntax tree or things like that. And the same is happening now with parsers. A library that's very, very recent has seen the light recently, and it's CTPG for compile time parser generator. And it's actually kind of having Yak or Bison inside of your compiler. So CTRE and CTPG are pretty complementary, because CTRE is more like kind of a lexer, and CTPG is actually the parser. So with these two combined, you can actually write proper compilers for proper languages. And CTPG supports ILR1 grammars, which are pretty powerful. So you can actually implement very powerful languages with that. So you should see right now that we are kind of going towards compile time compilers, and that metaprogramming is becoming easier over time. And is that really a good thing? Sorry. Well, I think it is. First of all, because we are getting better embedded domain-specific languages. So if you take Blaze, for example, it's a tool that's very easy to use for non-C++ savvy audiences, for people who are not familiar with SIMD optimization, with BLOS, or even with parallelism altogether. But yet it allows anybody to just write simple mathematical equations and get very high performance code as an output. It's also good because we get metaprograms that scale better. If we get regular C++ tools to generate code, it means that we can organize metaprograms the same way we organize regular programs, which is a good thing. And it also means that metaprogramming will become more mainstream over time, which is a very nice thing, I believe, because it will bring more people to the table to contribute to amazing projects. Because pretty often, a problem that's faced by metaprogramming libraries and others is that very few people are actually able to maintain them, because metaprogramming in its current state is kind of a niche practice. So yeah, I really believe it's a great thing for the C++ community altogether. However, with great constexpr power comes great compile time. Actually, we're not really sure about that, because, well, we don't have quite a lot of ways to measure compile times currently. So metaprogramming is almost on par with regular programming, but regular programming has debuggers, profilers, and it also has ways to benchmark code in a meaningful way and to get results that are meaningful and quantitative. And there is no such process for metaprograms. And also there is little to no science behind compile time rule of thumbs. So most of the rule of thumbs that are used to reduce compile times are actually kind of things that have been heard here and there on forums or on websites, but there is actually very few scientific literature on the matter, which is kind of the problem, because we need a sane process for understanding compile times in C++. And hopefully that's what we are going to bring with ctbench. So currently, what can we use to measure compile times? So in 2009, there's been templates. So we'll see what it is. It's written by Zoltan Barok-Nagy, Zoltan Porklub, and Joseph Mihalishka. There's been Metabench in 2016 by Louis Dion and Bruno Dutra. And then BuildBench in 2017 by Fred Tango. And obviously in 2019, there's been Clang Time Trace and Clang Build Analyzer by Aras Prankshevicius. Sorry if I misread some of the names here. I'm trying my best. So templates is kind of a big project, actually. It's meant to be a drop-in replacement for Clang. So you just use it instead of your compiler, and it provides you a lot of tools. It's basically a big profiler that's able to measure the time and memory usage of template instantiations. It also provides interactive debugging, but it's mostly just a one-shot profiler that you can use on one translation unit. And this is kind of a problem because you cannot study, for example, complexities of certain metaprogramming practices or techniques. And there's also template tools which provide several conversion options. So you can generate instantiation graphs using GraphViz. You can export your data into XML formats, etc. So it's a pretty strong effort, actually, because you can also, I mean, not a lot of tools are able to properly measure template instantiation time and mostly memory usage. But another problem with template is that it doesn't provide any data about the impact on the backend of some metaprogramming techniques, which is kind of a problem because metaprogramming can generate symbols, and these symbols have to be sometimes generated into code. So yeah, template is not complete in that regard. And then there's metabench. So metabench is a framework and also a set of benchmarks for C++ metaprogramming libraries. So it actually benchmarks most of the support libraries that I mentioned in my previous slide. It generates benchmarks using Ruby templates. So basically, you're not writing C++ code, but Ruby templates instead. It has what we are going to call a black box approach. So it only measures compiler execution time. It doesn't provide you an inside view of what's happening. Like it won't tell you how much memory a certain instantiation took, or the time a specific symbol took to compile. However, it supports all compilers, not just Clang, which is kind of a good thing. And it has a very nice web export function. I mean, that's basically how you read the results. So it provides pretty valuable data, but it's kind of harder to reuse because it's a framework and not a library. You cannot integrate it properly in your own projects. Then we have buildbench, written by Fred Tango. It's been around since 2017. It provides you a very simple web interface to easily write code. It has a black box approach, so it's not going into the details of what's happening either. It does support all compilers, and it also allows you to compare one-shot benchmarks. So as opposed to metabench, which allows you to trace graphs with variable size benchmarks, this one only allows you to run one benchmark. So this is what I call one-shot benchmarks. And also it allows you to make per compiler comparisons possible. So you can compare a similar C++ code compiled by Clang or GCC, and it will do the compiler benchmark for you. So it's pretty nice to play with. It's pretty nice to get an idea of what works or what doesn't work. But it's not extensive enough to really get a broad base of knowledge about compile time. And then there's been Clang time trace since 2019. So this approach is very interesting because it's actually provided by Clang. So if you have Clang, you have this feature and you can just emit time trace files. It outputs flame graph JSON files for Chrome tracing. So Chrome tracing shows you the flame graphs and show you like how much time was spent in each pass and all the sub-passes. It breaks down the compiled passes for every symbol. It's not, the symbols aren't mangled, so it's pretty easy to work with. And also what's interesting is that it works for both the front end and the back end. So you can benchmark the Clang instantiations, but also the LLVM, all the LLVM codes and stuff that can happen afterwards. So it has a very strong reuse potential and it's available pretty much everywhere. The only downside is that it's not available with GCC currently. There is an issue on the GCC tracker about that, but I'm not too sure that it will get implemented on GCC anytime soon. Okay, so Aros also wrote Clang Build Analyzer, which is a nice tool to use with time trace. It's basically just a user-friendly output for your time trace files. So it's just going to tell you if some symbol took more time to instantiate than others, and etc. It's very an essential view over the time trace files, and it's again not really fit for in-depth studies. Okay, so now we're going to talk about ctbench. So ctbench is a compile time benchmarking and also data analysis tool for Clang. It's also built on top of time trace, which is why it doesn't support GCC. It has repeatability and accuracy in mind because we wanted to provide a tool that's able to generate data for scientific reuse. It's able to generate variable size benchmarks, so not just one-shot benchmarks. And it's also very C++ developer friendly. It's easy to integrate and pretty easy to write C++ benchmarks because the benchmarks are only C++ codes, and actually the benchmarks are instantiated at several sizes thanks to the compiler. But we can just suppress the pre-processing time because we can actually measure it using time trace. It provides a pretty simple CMake API for declaring your benchmark targets. It takes care of all the dependency management and so on. And you can also configure the data extraction as well as the graphs themselves using JSON config files. A few ones are already provided because they're pretty verbose. You'll see how they look like during the presentation of the tool, but to be honest, I'd prefer users to just use the provided config files if they don't need to do any customization. However, if you want to do customization, all the docs are provided if you wish. So we're just going to talk about the methodology that ctbench implements. So in ctbench, we reason with benchmark sets, benchmark cases, benchmark iterations, and samples. A benchmark set is a collection of benchmark cases to compare. A benchmark case is a compilable C++ file, and it can be compiled several times for a given range of sizes, and it will generate a translation unit using the preprocessor, so that we can actually generate code to benchmark and to evaluate. And the benchmark iteration size is, well, passed as a preprocessor defined when compiling this C++ file. A benchmark iteration is the terminology we use to talk about a benchmark case that's been compiled, that will be compiled with a given size. And several samples are collected for each iteration size. So for example, you're gonna create a benchmark case, you're gonna instantiate it at several sizes and get several samples for each size. And one sample then is just one time trace file. So here's, I mean, just a graph that shows the order of inclusion for each structure. So a benchmark set contains benchmark cases, which contains several benchmark iterations, which themselves contain several samples. So here's what a C++ benchmark case looks like for ctbench. Here we implement a sum of variadic types. So we're just summing up compile time values stored in compile time uints. So I mean, it's just a constexpr container for unsigned ints. Here we have a recursive implementation for summing up values of these types. And then we have a benchmark driver that generates the code that we want to evaluate. So the benchmark driver just takes a benchmark size as an input, and it generates the sequence of code that has to be then instantiated. And then we have the same with another implementation that we want to compare it to. In this implementation, we're actually using expansion sum. So these are parameter pack expansions. It should be, in theory, more performant than the former implementation for several reasons, and we'll see why. And the benchmark driver is pretty much the same as the recursive version. So again, ctbench defines the benchmark size for each iteration size, and this is taken care of by the CMake API. So the CMake API looks like that. You have a benchmark declaration function. This is ctbench at benchmark. So you give it the target name, which is variadic sum.recursive. This is just like an arbitrary name. You can put whatever you want in that name. Then we have the benchmark file that we want to instantiate, and then we have the range parameters. So here we are starting from 1, ending at 32. So 1 is included for the node, and then we have the step amount. So it's going from 1 to 32 by increase of 1, and then we have the number of repetition for each and every iteration. So it's going to sample a total of 320 compilations. And then we have the graph declaration function, which is ctbench add graph. So again, you just give it a target name. Here you give it a config file, and then you mention the benchmark targets that you want to compare. So the graph declaration is going to take care of the dependencies, and afterwards you don't have to do anything. Also, optionally, if you need it, you can just bring your own flags using the ctbench add custom benchmarks, which I'm not going to detail here, but if you're interested in the tool, you can just look at the documentation and it should be fine. Okay, so now the JSON configs. So as I said, they're pretty verbose, so I'm just going to sum up what they contain. So they contain the graph options on one side, so you can select which plotter you want to use. Currently, we have a debug plotter, a simple curve plotter, so it's going to draw simple curves for a lot of features. And then we have stack curves, which is going to stack curves for each and every benchmark case. We have the output file formats, and there you can put pretty much anything that's supported by GNU-plot, thanks to the scplot library. We have the graph dimensions and other plotter-specific graph options. In the data options, we have defined named data groups. So this is the part that's the most interesting if you want to target your very own set of data. For example, you want to target very specific instantiation passes. So you can define named data groups and implement predicates to target those specific data. And the predicates that are available are pretty rich already. We have regex matching, JSON inclusion matching, logical operators, and so on. So basically, the regex matching takes a name, a pointer, like a JSON pointer that describes where to find the data that you're targeting, and also regex to tell it what kind of value you're expecting at the target. The JSON inclusion matching works by checking that all the members in the field that you gave it, in the JSON structure that you gave it, are present in the time trace events that you want to target. And then you have logical operators to make combinations of these predicates. So again, pre-made configurations are available, but if you want, you can just customize the existing ones. It's okay. And now I'm just going to take you to a quick tour of the tool itself. I'm not going to show you the insides of it, just how to use it. So again, I have my two implementations. So these are my two variadic sums. I have the recursive version, then the full expression version. And here I have, well, a few CMake variables to declare like the start, stop, and step for the iteration range. I have the number of repetitions. Here I declare the benchmarks, and then I just have to declare the graph. And all I have to do is to call Ninja with J1 parameter. Also, side notes on that, you should be calling Ninja with J1 because Ninja by default will parallelize these benchmarks. And you want to make sure that they don't run in parallel. And now we give it the name of the graph. So it's generating the graph because I already run the benchmarks. And while it's working, I'm going to show you what the config file looks like. So here we have the name of the plotter, which is the compare one. We have a few plotter-specific parameters such as draw average and draw points, if you want to draw only the average or only the points and so on. We have the output formats, the value that we want to target, the dimensions, and a few other things like legend title, X label, Y label, and so on. And here we have the group descriptors. So here I have one descriptor, which is the one that targets the execute compiler total time. And the predicates is a string equal predicate, which targets the name field and checks for that string. Okay, so now I'm going to show you the outputs of my graph. So I think it's actually compare. There it is. So these are the kind of curves that you are going to get with ctbench. So this is like the PNG output. This is a SVG output. We're going to have a look at the execute compiler. So this is pretty much what you would get with metabench. This is the total compiler execution time, but you can also get things like front end or backend curves, and do any kind of comparison you want. Okay, so back to the presentation. So now we already have a bit of literature on, I would say, C++ compile time rule of thumbs. There is one rule that's called the rule of heel, which is an ordering of the compile time impact of several metaprogramming techniques. So for example, the SFINAE would be the most expensive, and looking up a memos type would be the cheapest one. And between that, you have all things like instantiating a function template, instantiating a type, calling an alias, and so on. So this is a rule that's been present in Odin Holm's presentation at CPP now in 2017 called Type-Based Template Metaprogramming is Not Dead. And it's based on library implementation comparisons in Metabench. There is no actual project that allows you to strictly compare these the cost of these operations, which is kind of a problem, and that's the kind of things we wanted to solve with ctbench. And now I'm just going to show you what kind of benchmarks we can run. So I have another implementation, benchmark implementation. I'm just going to show you the code quickly. So we have a function selection that occurs. Okay, so right there. Okay, so we're calling foo with a parameter, with a template parameter, and foo will be a different function according to the template parameter. So we want to try to estimate the cost of a function selection using enable if with obviously a custom implementation to avoid including the whole type traits. The whole type traits include. We have enable if with an alias. We can use if constexpr, or we can also use requires. So we have again the same driver pretty much for all the implementations, and we declared all the benchmarks in the CMake as well as the control function. And now we are just declaring a few graphs, and we want to see what it looks like. Okay, so the first thing we were going to have a look at is the execute compiler time. So we can see that the if constexpr here, the if constexpr version is the cheapest one of all four. If constexpr, I guess, doesn't require as much work as the other ones, because you don't have to rely on expensive mechanisms such as SFINAE to implement to differentiate your functions. Then followed by that, you have requires, which is slightly more expensive. And then you have the two different enable if implementations. So enable if T is the one that's the most expensive, and enable if is the second most expensive. So this kind of goes in the same direction as the Uruf Heel, where it's said that SFINAE is actually pretty expensive. But the interesting part of ctbench is that we can actually look at more details, more detailed stuff. We can look at the front end time. So actually, the front end time is pretty much the same as the back end. I mean, it follows the same pattern, just not the same scale. So again, if constexpr is the cheapest one, then followed by requires, enable if, and enable if T. But then we can also look at the backend and see that these metaprogramming techniques don't put any pressure on the backend side. However, when we look at other benchmarks, such as the variadic sum, the implementations are here very different because they don't generate the same number of symbols. Well, first, the fold expression version is incredibly more cheap than the recursive version. And we can see that it's pretty much the same in the front end. But an interesting part is that it's also very different in the backend. So here the fold expression has a pretty close to constant cost for the backend, whereas the recursive version has a much more steep slope. So this underlines the fact that metaprogramming techniques don't have an impact just on instantiation times, but also on LLVM code generation. Okay, so now just for an overview of the project, because I don't want to get too much into the details of the code of ctbench. So on one side, we have the CMake API. We have benchmarking.cmake, which declares the end user API. The documentation is provided inside, and it can easily be extracted into a markdown file. Actually, there is a tool to do that. And then we have the Grapher subproject, which is kind of the meatiest part because it takes care of everything related to interpreting the data. It has a CLI driver. It has a time trace reading library, a predicate engine in the library too, and also all the plotters, all available as a library. So as I said, it's designed as CLI drivers on top of library projects. So it's kind of like Clang, where you have a lot of library code and then just a few lines, a few files to actually call and drive the library part. And it relies heavily on scplot, which is, by the way, an incredible plotting library if you're interested in that. Scplot only depends on GNU plots to generate plots, and it's so far the best one I've seen to easily generate 2D plots and export them. Also, new plotters can be written easily, and the output is not limited to GNU plots. I think I'm going to write, I have projects to write CSV export plotters. So basically there is a unified interface for plotters. It just takes a set of benchmarks, of benchmark data. It also takes a config and just outputs whatever you want. So another step to improve ctbench would be to write, for example, a CSV export or something else just to generate files that are easier to work with than JSON or pre-made graphs. And on the tooling side, we have time trace wrapper, which is just a wrapper for the Clang executable. It's used to get the outputs arguments, which is not possible using pure CMake. Actually, generator expressions don't allow you to get output file directories wherever you want. So I had to write this tool. And I also have a tool that allows me to extract the API doc into a markdown file. Okay, so just to sum it up, what is the purpose of ctbench? Well, it's meant to bring better measurements and analysis tools where it's lacking. Well, obviously it's not complete, and it's I'm not meaning that other tools are useless. Obviously they are useful because, well, ctbench doesn't support GCC, but ctbench allows to get a better understanding of compile times, to get our hands deeper into what Clang does during compile time. So now what do we have? We have a flexible tool sets to run and analyze Clang and LLVM compile time benchmarks. And is it perfect? Well, it is not, because first, time trace has blind spots. Some functions aren't included in the time scopes. So whenever you're trying to aggregate data, just keep that in mind. And obviously, we cannot ignore GCC as it is the major C++ compiler. Obviously, we cannot ignore MSVC either, but this is a more Unix-focused tool. So we'll see maybe in the future for Windows support, but it's not on my plans. So thank you for coming to my talk. I'll start to read the questions. If you want to have a look at the projects, well, here's the link, so you can have a look at the documentation or the code or whatever you want. And I'll start reading your questions. Okay, so Q&A. Yeah, Well, as I said, MSVC, well, this is a more Unix-focused tool because I'm the only one working on that tool, and I don't really have any machine to run Windows tests. So, I mean, that's just the way it is for the moment. And if someone wants to contribute to the project and try to bring MSVC supports, I'll be happy with it. However, my priority would be to have support for GCC because it's, well, the one that's used the most on Unix platforms. And also it's free, and so is Unix. So that's why I prefer to have GCC support first. Okay, so time-based matrix, can you also get? Okay, so currently there is no way in TimeTrace to get the amount of memory that's taken by template instantiations and so on. It's limited to the output of TimeTrace, but you can eventually target TimeTrace events that aggregates other events. And that includes, for example, the number of instantiations and so on. So actually, you could do it in the current state by just changing the value JSON pointer, change it to, I guess it's number or something. If you target aggregate events, it's okay, but otherwise you have to write your own plotter. But it's easy to just hack into it, so it shouldn't be a problem. But even though I still plan to improve the current plotters and allow people to define which kind of aggregates they want to use over TimeTrace events. Hopefully that answers your question. So any other question? In theory, you can, because the TimeTrace events contain all the information. I'm going to try to just bring that up. Variate exam function selection. Okay, I'm going to try to have a look at this one. This one seems to be pretty meaty. Okay, it's taking some time. So for example, if you look at the TimeTrace events, there is actually an args part which contains stuff like, well, in the case of source TimeTrace events, it contains the name of the C++ file that's included. And if you go in instantiate functions, you can just have a look at the symbols. I mean, you can filter on the symbols, and these kinds of information can be targeted using JSON pointers, JSON pointer predicates, or JSON value predicates. So hopefully that answers your question. But really, ctbench has been thought to be as flexible as possible. And this is why the configuration files are so complex and so verbose. This is because I was expecting, well, myself and maybe other people to try to observe various data. And hopefully that's good enough for most people. Okay, so we still have some time for other questions. I'll wait a few minutes, and if nobody has any question, then I'll just go back to Discord for the rest of well, the presentation time. I'm just gonna have a look at the dismissed ones. Okay, so these are the ones for the previous presentation. Okay. Okay, so again, here's the link to the GitHub project if you're interested in having a look at ctbench or contributing or whatever, or just integrating it in your projects. So just as a side note, it should be pretty easy to integrate using CMake because it just uses fetch contents. Another thing I would like to do is to provide a more packageable project in the future so that it can be packaged into stuff like, well, VC package or Conan or other system package managers.